The Pareto distribution, named after the Italian civil engineer, economist, and sociologist Vilfredo Pareto, is a power law probability distribution that is used in description of social, scientific, geophysical, actuarial, and many other types of observable phenomena. Definition: if X is a random variable with a Pareto distribution, then the probability that X is greater than some number X, that is the survival function, is given by where xm is the minimum possible value of X, and I plus or minus is a positive parameter. The Pareto type I distribution is characterized by a scale parameter xm and a shape parameter I plus or minus, which is known as the tail index. When this distribution is used to model the distribution of wealth, then the parameter I plus or minus is called the Pareto index. Properties: cumulative distribution function. From the definition, the cumulative distribution function of a Pareto random variable with parameters I plus or minus and xm is. When plotted on linear axes, the distribution assumes the familiar J-shaped curve which approaches each of the orthogonal axes asymptotically. All segments of the curve are self-similar. When plotted in a log-log plot, the distribution is represented by a straight line. Probability density function: it follows that the probability density function is moments and characteristic function. The expected value of a random variable following a Pareto distribution is. The variance of a random variable following a Pareto distribution is. If I plus or minus a per mil 1 currency, the variance does not exist. The raw moments are. The moment-generating function is only defined for non-positive values tau per mil 0 as. The characteristic function is given by where ax, is the incomplete gamma function. Conditional distributions: the conditional probability distribution of a Pareto distributed random variable, given the event that it is greater than or equal to a particular number x1 exceeding xm, is a Pareto distribution with the same Pareto index I plus or minus but with minimum x1 instead of xm. A characterization theorem: suppose x1, x2, x3 are independent identically distributed random variables whose probability distribution is supported on the interval xm, aa, for some xma a0. Suppose that for all n, the two random variables min x1, a, xn and min x1, a, xn are independent. Then the common distribution is a Pareto distribution. Geometric mean: the geometric mean is. Harmonic mean: the harmonic mean is. Generalized Pareto distributions. There is a hierarchy of Pareto distributions known as Pareto type I, II, III, IV, and Feller-Pareto distributions. Pareto type IV contains Pareto type II as special cases. The Feller-Pareto distribution generalizes Pareto type IV. Pareto type IV. The Pareto distribution hierarchy is summarized in the next table comparing the survival functions. When I1/4 equals 0, the Pareto distribution type II is also known as the Lomax distribution. In this section, the symbol xm, used before to indicate the minimum value of x, is replaced by I florin. The shape parameter I plus or minus is the tail index, I1/4 is location, I florin is scale, I cubed is an inequality parameter. Some special cases of Pareto type are the finiteness of the mean, and the existence and the finiteness of the variance depend on the tail index I plus or minus. In particular, fractional I moments are finite for some I0, as shown in the table below, where I is not necessarily an integer. Feller-Pareto distribution: Feller defines a Pareto variable by transformation y equals a y1 a1 of a beta random variable y, whose probability density function is where b, a is the beta function. If then W has a Feller-Pareto distribution Fp, I1/4, I florin, I cubed 1, I cubed 2. If and are independent gamma variables, another construction of a Feller-Pareto variable is. And we write WFP, I1/4, I florin, I cubed, I1, I2. Special cases of the Pareto distribution are applications. Pareto originally used this distribution to describe the allocation of wealth among individuals, since it seemed to show rather well the way that a larger portion of the wealth of any society is owned by a smaller percentage of the people in that society. He also used it to describe distribution of income. This idea is sometimes expressed more simply as the Pareto principle or the 80-20 rule, which says that 20% of the population controls 80% of the wealth. However, the 80-20 rule corresponds to a particular value of I plus or minus, and in fact, Pareto's data on British income taxes in his Cowes da Copyright Economie Politique indicates that about 30% of the population had about 70% of the income. The probability density function graph at the beginning of this article shows that the probability, or fraction of the population that owns a small amount of wealth per person is rather high, and then decreases steadily as wealth increases. This distribution is not limited to describing wealth or income, but to many situations in which an equilibrium is found in the distribution of the small to the large. The following examples are sometimes seen as approximately Pareto distributed: the sizes of human settlements, file size distribution of Internet traffic which uses the TCP protocol, hard disk drive error rates, clusters of Bose-Einstein condensate near absolute zero, the values of oil reserves in oil fields, the length distribution in jobs assigned supercomputers, the standardized price returns on individual stocks. Sizes of sand particles, sizes of meteorites, numbers of species per genus, areas burnt in forest fires, severity of large casualty losses for certain lines of business such as general liability, commercial auto, and workers' compensation. In hydrology, the Pareto distribution is applied to extreme events such as annually maximum one-day rainfalls and river discharges. The blue picture illustrates an example of fitting the Pareto distribution to ranked annually maximum one-day rainfalls, showing also the 90% confidence belt based on the binomial distribution. The rainfall data are represented by plotting positions as part of the cumulative frequency analysis. Relation to other distributions. Relation to the exponential distribution, the Pareto distribution is related to the exponential distribution as follows. If X is Pareto distributed with minimum xm and index I plus or minus, then is exponentially distributed with rate parameter I plus or minus. Equivalently, if Y is exponentially distributed with ratio I plus or minus, then is Pareto distributed with minimum xm and index I plus or minus. This can be shown using the standard change of variable techniques. The last expression is the cumulative distribution function of an exponential distribution with ratio I plus or minus. Relation to the log normal distribution. Note that the Pareto distribution and log normal distribution are alternative distributions for describing the same types of quantities. One of the connections between the two is that they are both the distributions of the exponential of random variables distributed according to other common distributions, respectively the exponential distribution and normal distribution. Relation to the generalized Pareto distribution. The Pareto distribution is a special case of the generalized Pareto distribution, which is a family of distributions of similar form, but containing an extra parameter in such a way that the support of the distribution is either bounded below, or bounded both above and below, with the Lomax distribution as a special case. This family also contains both the unshifted and shifted exponential distributions. The Pareto distribution with scale and shape is equivalent to the generalized Pareto distribution with location, scale and shape. Vice versa, one can get the Pareto distribution from the GPD by and. Relation to Zipf's law. Pareto distributions are continuous probability distributions. Zipf's law, also sometimes called the zeta distribution, may be thought of as a discrete counterpart of the Pareto distribution. Relation to the Pareto principle. The 80-20 law, according to which 20% of all people receive 80% of all income, and 20% of the most affluent 20% receive 80% of that 80%, and so on, holds precisely when the Pareto index I plus or minus equals a log 4, 5, and equals a log 5 / log 4, approximately 1.161. This result can be derived from the Lorenz curve formula given below. Moreover, the following have been shown to be mathematically equivalent. Income is distributed according to a Pareto distribution with index I plus or minus AA1. There is some number 0 AA per mil 1/2 such that 100 % of all people receive 100, 1 AAP, A% of all income, and similarly for every real null A0, 100 % of all people receive 100, 1 AAP, N% of all income. This does not apply only to income, but also to wealth, or to anything else that can be modeled by this distribution. This excludes Pareto distributions in which a 0 AAI plus or minus AA per mil 1, which, as noted above, have infinite expected value, and so cannot reasonably model income distribution. Lorenz curve and Gini coefficient. The Lorenz curve is often used to characterize income and wealth distributions. For any distribution, the Lorenz curve L, F, is written in terms of the PDFF or the CDFF as, where X, F, is the inverse of the CDF. For the Pareto distribution, and the Lorenz curve is calculated to be. Although the numerator and denominator in the expression for diverge for, their ratio does not, yielding L equals 0 in these cases, which yields a Gini coefficient of unity. Examples of the Lorenz curve for a number of Pareto distributions are shown in the graph on the right. The Gini coefficient is a measure of the deviation of the Lorenz curve from the equidistribution line, which is a line connecting 0, A0, and 1, A1, which is shown in black in the Lorenz plot on the right. Specifically, the Gini coefficient is twice the area between the Lorenz curve and the equidistribution line. The Gini coefficient for the Pareto distribution is then calculated to be. See Orberge 2005. Parameter estimation, the likelihood function for the Pareto distribution parameters I plus or minus and xm, given a sample x equals a, x1, ax2, a. xn, is. Therefore, the logarithmic likelihood function is. It can be seen that is monotonically increasing with xm, that is, the greater the value of xm, the greater the value of the likelihood function. Hence, since xa per million xm, we conclude that. To find the estimator for I plus or minus, we compute the corresponding partial derivative and determine where it is 0. Thus the maximum likelihood estimator for I plus or minus is. The expected statistical error is. Malik gives the exact joint distribution of. In particular, and are independent and is Pareto with scale parameter xm and shape parameter ni plus or minus, whereas has an inverse gamma distribution with shape and scale parameters na1 and ni plus or minus, respectively. Graphical representation, the characteristic curved long-tail distribution when plotted on a linear scale, masks the underlying simplicity of the function when plotted on a log-log graph, which then takes the form of a straight line with negative gradient. It follows from the formula for the probability density function that for xa per million xm. Since I plus or minus is positive, the gradient a, I plus or minus +1, is negative. Random sample generation, random samples can be generated using inverse transform sampling. Given a random variety drawn from the uniform distribution on the unit interval, 0, a1, the variety given by is Pareto distributed. If U is uniformly distributed on 0, a1, it can be exchanged with variance, bounded Pareto distribution. The bounded Pareto distribution has three parameters I plus or minus, L and H. As in the standard Pareto distribution, I plus or minus determines the shape. L denotes the minimal value, and H denotes the maximal value. The probability density function is where L per mil za per mil H, and I plus or minus AA0. Generating bounded Pareto random variables, if U is uniformly distributed on, then applying inverse transform method. Is a bounded Pareto distributed? Symmetric Pareto distribution. The symmetric Pareto distribution can be defined by the probability density function. It has a similar shape to a Pareto distribution for x, xm and is mirror symmetric about the vertical axis. See also, Bradford's law, Pareto analysis, Pareto efficiency, Pareto interpolation, power law probability distributions, traffic generation model, notes. References, M. O. Lorenz. Methods of measuring the concentration of wealth. Publications of the American Statistical Association 9, 209 a 219. Bibcode, 1905 PAM SA. 9209 LDOI, 10.230/2276207 Pareto v la courbe de la répartition de la richesse. In, Bizano G., editor. Œuvres complètes de Vilfredo Pareto. Geneva, Librairie Droz PPA 1 a 5. Pareto, v la leg de la demanda. Giornale degli Economisti, 10, 59 a 68. English translation in Rivista di Politica Economica, 87, 691 a 700. Pareto, v Causes da Copyright Économie Politique. Lausanne, ed. Rouge. External links, Gini's nuclear family/Rolf Auerberger copyright. In, International Conference to honor two eminent social scientists, May, 2005 a PDF, Haswinkel, Michiel, ed., Pareto Distribution, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Syntref-1C is a C program to generate synthetic packet traffic with bounded Pareto burst size and exponential interburst time. Self-similarity in World Wide Web traffic, evidence and possible causes / Mark E. Cravella and Azur Bestavros, Weierstein, Eric W., Pareto Distribution, MathWorld.